So my talk today is on distributed quantum computing with distributed fan-out operations. And the aim of this talk is just to consider how quantum circuits, when they are distributed over a collection of quantum nodes in a distributed quantum computing fashion, how to execute these distributed programs, quantum programs, if you like, these distributed quantum circuits efficiently. So when we are trying to scale the quantum computation, it does require distributing qubits across nodes. And so we know that there are some difficulties with monolithic processors, given that it's hard to squeeze a number of qubits into that one QPU, if you like. There are a number of challenges. People are still working on that problem. But another way to scale the number of qubits that a quantum computation can employ is to use the qubits distributed over a collection of quantum nodes. Of course, that means it requires some way to connect the qubits located on different nodes. And the way to do this, one is to either use teleportation or teleporting qubit states from one node to another, or another way to do this is to use non-local 2-qubit gates or non-local multi-qubit gates, if you like. Non-local as in the qubits are on different nodes. And there are a number of, uh, there's a lot of work actually in this area now using entangled pairs to facilitate non-local 2-qubit gates such as non-local C0 or CZ gates. And there are already some experiments that showed that could work. But what we are exploring in this paper, instead of just using bell pairs, you still need to use some bell pairs, but can you also use GHZ states and the generalized GHZ states of this form, which would allow us to if you like, compress a sequence or a series of C0 gates into one multi-qubit gate operation, and hence reducing the depth of circuits quite significantly. So that's what we're going to do, right? So can you use some resource states like GHZ states to enable efficient distributed operations? Of course, we can't do without pairwise operations, and of course, bell pairs are just, if you like, is a minimum case, if you like, of a GHZ state, right? In some ways, but can we use multipartite gates, if you like? Okay. So if you think of an operation, right? So if you think of a circuit, something like the one below here, something like the one below here on the bottom right corner here, you can see that if you want to distribute this circuit, let's say 1 qubit per node, right? So all the examples that I'm going to talk about in this talk, for simplicity and just to emphasize the ideas, we're just going to use 1 qubit per node. So imagine you have 4 nodes and 4 qubits, C, T1, T2, T3, one on each node. And what we want to do is to execute this sequence of C0 operations, right? Or not really C0, or control U1, control U2, and control U3 operations more generally, right? And of course, when the U's are X, then you got C0 operations. So one way to execute this is to just use 3 bell pairs. Just use 3 bell pairs, and then when we use 3 bell pairs, we then are able to do 3 non-local control U operations, right? And that's the circuit for distributed control U. In this case, it's a control X operation, but the same thing with control U operation, right? So instead of using an X here, we put the U operation here, right? And that's how we can do non-local control U operation with the uh, resource of a bell pair, and this bell pair is indicated here, right? So you need, on each node, you need an additional qubit to to be involved in this bell pair, right? For this operation sequence of operations to work. So in this case, we need 3 bell pairs, right? But if we use an alternative gate and a GHZ state, we'll see that instead of 3 bell pairs, we just need 1 GHZ state, and which is distributed across the 4 nodes, right? And imagine if there are n of such operations over n nodes, you can collapse all that into a large GHZ state, use a large GHZ state and a large, what we call distributed fan-out operation, and do that in just one step, if you like. So that's the D fan out approach. So instead of n bell pairs like we use here, we just use one n plus one qubit distributed GHZ state, and then we can do that in one shot in O1 depth. And indeed, there's a lot of work, as I mentioned in the previous slide, that's trying to implement GHZ states in one shot or in one step, right? So one way to implement GHZ state is to realize a GHZ state is to use a number of bell pairs, right? Let's say it could be logarithmic number of bell pairs to generate a GHZ state. Or if you use a one-shot approach, if that is really realized, we can actually do create a GHZ state in O1 depth and therefore do a D fan out operation, which just uses one DGHZ state in O1 depth, right? So you can imagine there's a tremendous performance gain as a result, right? And what we can also see here, this is the typical fan-out operation, and here is how you can implement a distributed fan-out, assuming one computation qubit per node, and is aided by the extra communication qubits, as sometimes they are known, for example, A naught, A1, A2, and A3, right? These four qubits, A naught, A1, A2, and A3, are involved in a GHZ state, a 4-qubit GHZ state. And supported by that, with a sequence of operations like this, you would be able to do it in one shot. You can actually implement the distributed fan-out operation. Of course, in this case, it's not exactly O1. It is a constant depth. It's an O1 depth. There's a sequence of operations, so it's not a depth of one, but at least it's O1 depth. Right, so no matter how many nodes are involved, how many qubits are involved in a D fan-out, you can get a constant depth operation for a distributed fan-out. Right. So, okay, all well and good, but the question is then when can you use such a distributed fan-out operation, right? So it's tremendous savings, right? N can be extremely large, can be 100 or 200, let's say, right? And you collapse that into a constant depth circuit. So, very good, but where do you see a distributed fan-out operation, right? Is it common, right? And that's the question we may ask. So if we look at okay, I'll close this. I'll show a series of examples that indeed the fan-out operation does arise in quite a number of places, as the paper shows. And you just use some simplifying notation. So a DC NOT gate, I just use this simple simplified notation on the right here. And also on here, instead of the distributed fan-out gadget that you see here, I just simplify it to this notation here on the right. Okay, so we see in a distributed quantum Fourier transform operations, right? So you can a bit of rewriting. You can write a quantum Fourier transform, just excluding the swap gates at the end, swap operations at the end. Suppose you just do a quantum Fourier transform and using these gate operations, and you can see quite the pattern here, right? These three p pi over 2, the phase gate p pi over 4, p pi over 8, they can collapse into one D fan out operation, and then p pi over 2, p pi over 4, the next one, the one after the Hadamard operations in a D fan out. And this is, of course, a if you like the simplest version of D fan out, which is actually a DC not operation, a DCU operation. And then, so you can see, right, that you can actually use D fan out here for distributed QFT. You can also look at another circuit. Let's say this is a circuit to compute a unitary of this form, which is typically found in QAOA operations, and supposed to do a distributed QAOA quantum approximate optimization algorithm. And then you can rewrite it, that this gate operation into this form using the controlled phase operation, and it looks like this. So let me just, so it looks something like this gate operation. And then if you put together a sequence of this gate, let's say in this example, is just a sequence of 3 operations of this form, and it looks like this. And then you can move the outside operations to the end, and then you can see this familiar pattern of a distributed fan-out operation. And then you can then implement this operation here using this as shown in this figure here, right? So these 3 control P operations, control phase operations, become just one fan-out operation or one distributed fan-out operation, and then followed by all local operations. So pretty efficient. Here's another example in parity operations. So if you generalize the example previously, and we want to deal with any n-qubit unitary operation of this form, e to the I minus I summation of some constant of Pauli operation, a Pauli string, and then you can then consider implementing a unitary of this form, right? When applied to a computational basis, we get this, right? So effectively, if you have e to the minus I theta z1 to zn, we are doing a parity operation, right? And a parity operation looks a bit like this, but you can convert a parity operation into um, using the Hadamard gate, you can convert it into a fan-out operation, right? And this is well known from the reference. And then with this, you can actually replace this sequence of controlled C0 operations in the middle here between the Hadamard gates with a distributed fan-out operation, right? So that's what you get. So we can use this to implement any n-qubit unitary operation actually. So it can be realized using this form. Okay, so, and this is a recent work on encrypted cloning, right? So not actually the cloning as in a typical clone, but encrypted cloning has been made possible. There's a reference of that in 18. So you can actually encrypt create encrypted clones of so not clones, but encrypted clones of a particular qubit operation. And if you want to do that in distributed fashion, it involves computing a distributed version of this encoding unitary, right, as shown here. And so it's actually, now you can see that these two operate, these operation, the encoding unitary is very similar to the form that we saw previously. And certainly we can realize this using a distributed fan-out operation, or at least with a couple of distributed fan-out operations. In fact, you can use two here. We can then quite efficiently implement this inside almost as I mentioned, with respect to n, a constant time. So in general, right, we want to be able to take any quantum circuit expressed using C0 operations, let's say, and single qubit unitaries, and we should be able to then convert that into a distributed fan-out to be a quantum circuit that uses as many distributed fan-out operations as possible. And then when you distribute it, we can use D fan-out, and therefore reduce the depth of operations quite significantly, right? So that's the idea that we want to be able to do. And of course, generally, it's quite a hard problem, right? Take any quantum circuit, convert it into one that uses D fan-out. And there's a bit of software called fan-out packer that packs C0 gates into fan-out. And there are certain heuristics or rules that you can use in order to do this. So basically, if it analyzes a quantum circuit, if there any part of the circuit where there's a sequence of C0 gates, you can collapse it into one fan-out operation, right? And sometimes you may need to do a bit of gate reordering. So if you look at this example, the CGR, the input for this example is a CX gate followed by H, another CX gate, RZ, and another CX gate. But it turns out that some of these gates can commute, right? So you move the H and the RZ gate to the end here, and then you get the CX0 to 1, CX0 to 2, and CX0 to 3 all adjacent to each other, and then which then converts into you get a sequence of CX gate, which according to the rule then converts into one fan-out operation. So sometimes you can swap gates around, right? And we draw inspiration from one of the papers, and has been using this idea of gate reordering, right, in order to find and pack out as many fan-out operations as we can. Okay, so we want to develop the compilers that can do this very efficiently. We are just on the way to a simple tool in the GitHub that does this kind of gate reordering if needed in order to pack out some fan-out operations. So there's a proof of concept there, but we can go further to explore trade-offs. And then we can explore communication qubit requirements of different applications and see which one can gain the most from packing into D fan-out operations. We can work with logical qubits, right? We haven't looked at quantum error corrected qubits yet. And then, so this is what we are looking at this time. And then hardware implementations of all this. Of course, it all relies a lot on being able to create GSX state efficiently. Thank you very much.